previously we discussed how X-rays are produced. That typically you have an electron which is accelerated by a large potential difference that then slams into a target, and the electron's kinetic energy turns into the energy of a photon, an X-ray photon. Now normally this produces a spectrum of X-rays, and so there's a broad spectrum of X-rays that can be produced. But if you make a graph of the spectrum of X-rays produced in this manner, in addition to this broad spectrum, you will see characteristic X-rays, specific lines at specific wavelengths that are indicative of what kind of metal target the electron was running into. Now, these characteristic X-rays are produced when the electron comes in and it strikes one of the electrons in the atom of the target. So it will come in really fast and it will strike an electron in one of the inner energy levels of the target atom. And then this electron goes flying off. So it's completely knocked out of the atom since the incoming electron has so much energy. But then, since this electron has gone away, the electrons in the higher energy levels look down and say, there's a place where I could be. They jump down and then they emit a photon at one of these characteristic X-ray wavelengths. So these characteristic X-rays correspond to the energy level differences between the energy levels in the target atom. So the lines that you get have specific names depending on where the electron that jumps down came from and where it's headed to. So if you have an n equals 2 electron, so an electron in the n equals 2 level, so that's its shell, if a n equals 2 electron fills a vacancy in n equals 1, we call that a K alpha line. And this is because the first shell is sometimes referred to as the K shell. And if it's the n equals 2 electron, it's called the K alpha line because that's the first line that you can produce. That's the smallest energy gap between the n equals 2 level and n equals 1. If you're coming from n equals 3, then that's known as the K beta line. If you have electrons jumping down to fill vacancies in the n equals 2 energy level, if it's from that first energy level above, so n equals 3, then that's known as the L alpha line because the n equals 2 shell is sometimes called the L shell. So that's the L alpha line, and if you're jumping from n equals 4 to n equals 2, that's the L beta line. Now we want to figure out what the energy levels are so we can calculate where these characteristic X-rays should appear. So what wavelengths should they have? But as we mentioned before, when you're dealing with an atom with more than one electron, it's nearly an impossible problem because the electrons interact with each other. It's very, very difficult to predict the exact energy levels that they're going to have. However, we can use a technique for coming up with a rough estimate. So this is not going to be exact. You'll want to actually measure them to get an exact value or have a supercomputer ready to calculate more precisely the energy levels within this multi-electron atom. But we can use this technique for coming up with just a very rough estimate for what the energies of these characteristic X-rays should be. So once again, we're going to be looking at energy differences between energy levels, and we're going to make very, very rough estimates of what those energy levels are. Now, the energy calculations have to take into account electron shielding. So what that means is that if you have an electron out here in an outer energy level and it's looking down at this inner energy level, the energy that it has is dependent upon the charge of the nucleus. However, there's all these other electrons that are in lower energy levels that shield the nucleus with their negative charge. So it's like this electron is orbiting an atom, a nucleus with less charge less positive charge because it's somewhat negated by the electrons that are beneath the level where this electron is. So if you have an electron in the n equals 1 shell, then roughly the energy level is going to be equal to minus z squared, where this is the number of protons, times 13.6 electron volts. This isn't exact, but this is a rough estimate of what an electron sitting in the n equals 1 shell would see. Now, for an electron in the n equals 1 shell, it has an unimpeded view of the nucleus, and so we don't have to include any shielding effects. However, for an electron in the n equals 3 shell, then there is going to be some effective shielding. So we need to count how many electrons are in the shells below the n equals 3 shell. And we can see that we have one electron here. This one is missing because it got knocked out. And then we have a total of 1, 2, 3, 4, 5, 6, 7, 8 electrons in the n equals 2 shell. So there's a total of 9 electrons in shells below this electron. And so we subtract 9 off of the charge of the nucleus, so off of the number of protons. Then that gets squared and multiplied by 13.6 electron volts divided by n squared, where n would be equal to 3. So this is a very rough estimate of the energy that this electron has being in this n equals 3 shell. Then if this electron jumps down to fill the vacancy in the n equals 1 shell, the photon that is emitted is going to be roughly equal to the difference between these two energy levels. So let's look at an example problem where we can practice doing this. Say we have an electron dropping from the m equals shell, for the m shell, which is n equals 3, to a vacancy in the k shell, which is n equals 1, in a silver atom. What is the change in energy, which would become the energy of the photon? So in this case, we need to estimate the energy levels for both the n equals 3 and the n equals 1. So initially, the initial energy of this electron is going to be when it's in the n equals 3 energy level. So here we want to take minus, and then for the charge of the nucleus, well, we need to know the effective charge of the nucleus. So we have silver, which has 47 protons, so we have 47 units of charge, but then there are 9 electrons in the n equals 2 and n equals 1 energy levels. So n equals 2, there are 8 there for the p and s orbitals, and then there's an additional electron in the 1s orbital, and then so those combine together to shield the nucleus. So effectively, the charge in the n equals 3 energy level is going to see a nucleus with 47 minus 9 fundamental units of charge. This gets squared and then multiplied by 13.6 electron volts divided by n squared, and in this case n is 3. So divided by 3 squared, or 9. And that's going to give us an initial amount of energy equal to negative 2,182 electron volts. Next, let's look at the final energy level. So it's jumping down to fill the vacancy in n equals 1. So in this case, if you're in that first energy level, then there's no electrons beneath that are shielding. So we have 47 fundamental units of charge that the electron sees, squared times 13.6 electron volts, and then now we're in n equals 1, and then that gets squared. So if we do that calculation, we find that we have a final energy of negative, and this is going to be about 3 times 10 to the 4th electron volts. So finally, we need to find the energy difference. So we need to take the initial energy minus the final energy, And that energy difference is going to be 2.79 times 10 to the 4 electron volts. So that's the energy difference between the two energy levels, and as a result, that's going to be the energy of the photon that is emitted, at least in very rough terms.